Welcome to 7.1, Area Between Curves. This is our first day. So you will need your calculator handy as we're going to get some calculator practice. And our goal today is to find the area between curves. So we found the area underneath the curve, but now we're going to look at between the curves. So we're going to get our setup and we're going to finish this with our calculator, all right? So first, before we kind of get started, let this f of x, throw that into our y1, throw g of x into y2, and then we're going to take a look at this graph. And what we want to do is we want to find the area between these two curves, okay? So the g of x, that's our green, and the f of x is our blue. So we'll kind of talk about that. Okay, so remember, area underneath curves are just a bunch of rectangles added together, okay? So it's just a bunch of these rectangles, and I'm going to make mine bigger than it needs to be, right? But it's the sum of all these areas of these rectangles, and we're just adding up all these rectangles, these infinitely many rectangles together, okay? So how do we think about this? Well, the width of this rectangle is like our dx, okay? And the height of this rectangle is going to be this curve, this g of x, minus f of x, because it's our top minus the bottom, okay? The top curve minus the bottom curve, okay? But what do we notice over in this section, right? So we have to add this area to this area. So what changes over here? So if we were to draw that rectangle in, just to kind of visualize it, right? Again, this is much bigger than it really is. Our width is going to be that dx, and the height this time, that top, is going to be f of x minus the g of x. So that's how we can talk about the height of these rectangles here. So because my width is dx, then I need to talk about my limits of integration in terms of my x values. And where does it change? Well, I start when x is at -3 to x equals -1. At x equals -1, or anything to the right of -1, is where my rectangles shift in terms of the height. Now it's f of x minus g of x. So how does that help our setup? Well, if we take a look at our setup, we want the area from -3 to -1 of g of x minus f of x dx. Then we have to add that to the area of this second region. And that goes when x is -1 to +1. Okay, that's where it's enclosed. And this time it's f of x minus g of x. Now, if we were to kind of clean that up, g of x minus f of x would give us this polynomial. F of x minus g of x, all cleaned up, gives us this polynomial. But I want you to go back and practice on your calculator. So what you can do is, on your calculator, you can integrate from -3 to 1 of y2 minus y1, okay, dx, and see what you get. And you should get 12. All right, and then you're going to add that to the integral from, that should say -1, and then -1 to +1 of y1 minus y2 dx. So go ahead and try that on the calculator. You should get each of those integrals to equal 12, and therefore the total area between those curves is going to be 24. So just one thing to note all around is the area between two curves is really equal to the integral from a to b of f of x minus g of x dx, or you can think about it when we're talking with respect to x, top minus bottom. And we'll get into the next example, or the example 3 with that aspect. I want you to take a look at example 2, and I want you to see if you can set it up on your own. One thing we should look at is this graph, okay? So if you let y equals 4x plus 16, if you throw that into your y1, and then your y2 can be the 2x squared plus 10. So we want to find the area between these curves, but what we should notice is now there's 3 different portions. So if you're drawing a rectangle between these, what are we looking at, right? That might help kind of distinguish top versus bottom in these 3 different regions. So go ahead, try to set up, and you can go ahead and use your calculator to integrate it and get your final answer. Come back and check when you're done. Okay, looking at it, my first region went from -2 to -1 for my x values, and I had y2 minus y1, top minus bottom. This second region, now my top and my bottom flip. So I'm going from my x values of -1 to 3, and this time it's y1 minus y2. Then my third region, again they flip back. Now it's my red over my blue. So I'm going from 3 to 5, that's my enclosed region, of y2 minus y1 dx. And so if you were to plug each of these different integrals onto your calculator, you would get that first one to be 14/3, the second and the third, both 64/3. When you add these all together, you get your final answer of 142/3. This next example, we're going to look at 2 different ways to find the area between curves. All right, so if we're looking at our 2 equations, x equals 1/2 y squared minus 3, and y equals x minus 1. And we're going to integrate it first with respect to x, and then with respect to y. So we've been doing this with respect to x on the last 2 examples. So I'm going to zoom in just a little bit. And remember, when it's with respect to x, it's top minus bottom, okay? So as you're drawing your rectangles, you want to compare the top of the rectangle to the bottom of the rectangle. And your regions change when either the top and or the bottom changes, okay? That tells us we've got a new region to find the area for. We have to change our functions around, okay? So what I noticed is if I drew a vertical rectangle, so that's the green portion, okay? If I were to draw that rectangle, all of a sudden when I get to this portion here, this vertical green line, I notice that my rectangle, the top stays the same, but the bottom is now touching this purple line. So I'm going to have 2 regions to find the area for with respect to x, okay? Now, when our equations, or when we're finding the integral or the area with respect to x, my equations need to be y equals, or y in terms of x. So what we needed to do was we needed to change this equation so that I could solve for y. So the first thing I did was I multiplied everything by 2. And so we get 2x equals y squared minus 6. When I solve for y, I add 6 and then take the square root. So y1 is what I'm going to plug in, is really equal to plus or minus the square root of 2x plus 6. Okay? Now, we have to talk about this plus or minus aspect. And remember, with those even functions, we could essentially talk about this portion just being doubled. If I focus on the positive portion, I really just need to double that to get this bottom area. So we're going to think about that when we set up our area formula. y2 is already in terms of x, so we can just say y2 is equal to x minus 1. Now, if we're setting up our areas, remember, or our formulas, we have this area here, and we're going to add it to that second area over here. Okay, so those are our two distinct areas that we're adding together with respect to x. So the first region, this yellow region, goes when x is -3 to when x equals -1. And we're going to, it's my top of my rectangle hits the orange and my bottom hits the orange. So if I'm looking at it, this is where I said, well, we can just find the area of this guy, but we have to double it. So it's 2 times that square root of 2x plus 6. Okay, my second integral goes from the x values of -1 to +5. Okay, looking at my rectangle that we drew, the top is orange, the bottom is the purple. So we have our y1 minus our y2. Make sure you put parentheses around that function because we have to distribute that negative. Now you can go ahead and use your calculator to integrate this and double check that you get 18. Now let's shift gears and talk about finding the area between these two curves, but with respect to y. Okay, so with respect to x, it was top minus bottom. So the higher minus the lower. With respect to y, we go right side minus the left side. So now our rectangles are going to be horizontal. Okay, if we zoom in, we're focusing on that pink aspect now. And what we should notice is now the width of that rectangle is going to be dy. Okay, that dy portion, and the height of this rectangle is going to be the right side minus the left side. So we're talking about those different x values. Okay, so when x equals the purple minus when x equals the orange. So what that means with our equations is now our equations need to be x equals in terms of y. Okay, so that's our difference. So when we do that, this orange guy is already good. The purple, we need to just add 1 to both sides. So we get x2 to be y plus 1. Okay, so now as we draw our rectangles, what we can notice is that the right side always is the purple and the left side is always the orange. So we are just finding the area of one big region here, okay? We don't need to break it up like we did when it was with respect to x. So this time, our limits of integration are focusing on the y values. We're going from when y equals -2 to +4. So that should say -2. I apologize about that. -2 to +4, okay? So as we do this, we have our purple minus our orange, all right? And our purple is y plus 1 minus y 1/2 y squared minus 3. When we clean that up, we get our polynomial here, -1/2 y squared plus y plus 4. We're integrating from -2 to 4. And we can go ahead and integrate this easily. We'll do this one by hand, all right? And you can follow through. Now when we evaluate, when y is 4, we get this here. When y is -2, we're going to get this region here. And the good news is our ultimate answer is going to be the same as what we said when it was with respect to x. What I find very helpful when we're finding area between two curves is draw your rectangles. You can draw your vertical rectangles when you're talking with respect to x, and your horizontal rectangles when you're talking with respect to y. That helps you visualize which is the top minus the bottom, or the right minus the left with respect to y. This very last example, I want you to find b such that x equals b divides the region bounded by x equals 1, x equals 7, y equals 0, and the line y equals 3x minus 1 into equal areas. First thing I want you to do is draw the bounded region. So graph this situation and see what your bounded region is. After you do that, check back. Okay, so you should have gotten this region, all right? And what this question is asking us to do is it wants us to find some b value, all right, where x equals b, such that region 1 is equal to the area of region 2, okay? So essentially, if we're thinking about our rectangles and finding the area, it's probably going to be easier to write the areas in terms of with respect to x, okay? So if that's our dx, and then we have this rectangle here. So what I want you to do is I want you to set up your two integrals for finding the area of region 1 and region 2. And what you're going to do is you're going to set up when the integral of region 1 equals the integral of region 2. So try that and check back in just a second. Okay, so our first integral goes from when x equals 1 to when x equals b. That's where we're dividing up this region. And it's going to be our orange minus our purple. Well, our orange is that 3x minus 1, or y equals 3x minus 1. And the other one is when y equals 0. So we don't necessarily need this part, but for today it helps us visualize. And we want to set that equal to the integral from b to 7, because that's where the end of our region is. Again, it's still orange minus purple. So now we can go ahead and integrate these two values, okay? This first integral goes from 1 to b, and when we clean that up, we're going to get 3 halves b squared minus b minus 3 halves plus 1. And when we integrate this second one, or evaluate this second portion, we're going to get this right here. Cleaning things up, making it easier on ourselves, we can just multiply everything by 2. And when we do that, we're down to this function here. And it turns out to be a nice quadratic. So 6b squared minus 4b minus 134 equals 0, which we can divide everything by 2 here to get that quadratic. It doesn't factor, so we have to use the quadratic formula, okay? And we get 2 plus or minus the square root of, turns out to be 808 underneath, all over 6. But we're talking about a positive x value here, so a positive b value. So I don't need that plus or minus portion. I'm just worried about the plus portion of it. And so we do that, and we get our final answer of about 5.07089, or our exact answer of 1 plus root 2 over 202 all over 3. So that x value is what divides this entire region into 2 equal areas. We'll talk about these homework hints in class, so don't worry about those. If you have questions, let me know.